Part 8.3, Evaluate polynomials. In this part, we will solve our first problem in this class. Problem number 1, evaluate a polynomial. First, let me give you the problem first. Given a polynomial, p of x equals this expression. So I think you're familiar with this. Here, the coefficients a0 through an. And x is the variable. The question we need to answer, how to evaluate p of x efficiently. That's the problem. Now I think after you see this question, I believe most of you know how to solve. But here I want to remind you, although you may know how to solve, but think about this efficiently. You need to ask yourself, can you solve it efficiently? Or is your solution efficient? You can think about that. All right, so let's look at analysis. Here, for this particular problem, do we really need an algorithm here? If it is so easy, why we need a special algorithm? Right? So the first question. Let's try to look at the details. To evaluate a polynomial, we only need to do two types of operations, addition and multiplication. Okay, so we know very easy to do those operations. We can easily write a computer program to do it. Okay, all right. Now the question. In order to answer the question if your polynomial is efficient, if your algorithm to solve this problem is efficient or not, you need to answer this question: how to measure efficiency. What do you mean efficiency? What is the measure of the efficiency here? So we need to answer this question. Can we use the execution time? So one way to measure efficiency, the straightforward way, is execution time. But if you try to think about all the possibilities related to this execution time, you can see this is not a good measure. Because when we run the same program on different computers, okay, so if you clock it, if you record the execution time, I believe each one will give me different answer. Now, some students may give me 0.005 milliseconds. For example, right? Another, different. Everyone would give me different answer. If there is no consistent measure, how do we talk about efficiency? Right? So that's not a good one. That's not a good measure. So we should not use that. All right. So then the question, you can see we have a better answer using number of additions and multiplications. That will be a better idea because no matter what machine you use, for everyone, if you can count number of additions and number of multiplications, everyone will give me the same answer. So this measure is consistent. So that means we should do the efficiency measurement using this way. All right, yeah. So that's the first thing. After the analysis, we agree on this. All right, next, let's try to solve it. The first try, let's try to, count the number of additions, number of multiplications first. Okay. All right, we just use the straightforward method. Yeah, I think you know the meaning. What's the straightforward method? Yeah. Just do it directly. Yeah. All right. When we do that, we need to find each term, the value of each term. All right, so one term, each term. Find the value of each term. The general expression is this: a sub k times x to the kth power. Okay, yeah. We need to find its value with multiplication. We only need to use multiplications to get an answer. After that, then we add up all the values of the terms, we get the answer. That's the straightforward way. Okay, yeah. And this problem, I want to give you the reference on our textbook, section 6.5, page 234. Yeah. Here you can see I do not follow the natural order of the textbook. Yeah, because for this particular topic, here I want to show you the power of algorithm. So I feel this example is the best one to show you the power of algorithm. So I just move from section 6.5 to our first class. All right. Question: is your algorithm efficient? Right? Yeah. At this point, you may not have enough information. It could be too early to answer this question. Yeah. So, because at this point, if we ask this question, are we satisfied with the solution? It's not easy to answer this question. By impression, by intuition, most of you may feel it's okay. It's not a bad solution. It's acceptable, things like that. But it's hard to give a precise answer. If there is no comparison, how do you know it's good or not? If nobody can find a better algorithm, then you will accept this one. If someone can find a much better one, then nobody will feel this is a good one, right? So things like this. Yeah. So that's why it's not easy to answer the question at this point. Yeah. So we do not know how bad it is until we collect sufficient evidence. So later we will do it. Yeah. All right. Now we set our next step objective. Next step, we need to do something objective. Find the performance number of this algorithm. Performance number, specifically the number of additions and the number of multiplications. So that's the next step we need to do. All right. Now, let's do the counting. Our goal is finding the number of operations. Okay. In order to solve this problem, we need to add some assumptions. Let me tell you why we can do it. it is allowed to add reasonable assumptions when we solve real-world problems. Many times we need to do this. Yeah. But when we do that, the added assumptions should not alter the original problem significantly. Otherwise, you'll change the problem. And we don't want to change the problem. We want to solve the same problem. Right? So with that, now let's do some assumptions here. First one, we assume each addition takes 1 unit of time for simplicity. The specific time may not be that important, just 1 unit. Right? And each multiplication takes 10 units of time, 10 to 1 ratio. This assumption is reasonable because if people really look at the CPU, inside the CPU, approximately the ratio is like that, 10 to 1 ratio. We do not need very precise ratio. Approximate ratio is fine. Yeah. So regarding the unit, here I like to give you a little more information. Here the unit means certain number of nanoseconds. Yeah. So if you look at the CPU, the real exact time, a certain number of nanoseconds. Yeah. Yeah. Even approximately 1 nanosecond. Yeah. Because the CPU becomes better and better. Yeah. And here this nanosecond, I hope you know it, 1 nanosecond equals 10 to the negative 9th of second. 1 billionth, in other words, 1 billionth of a second. Okay. All right. Because with these two assumptions, it simplifies the whole setting without changing the difficulty of the problem. Still, so I think we didn't alter the original problem. We solved the same problem. Yeah. All right. Now let's do the work. All right. To do the work, do the counting. Here we need to use the discrete math. So that's why discrete math is the prerequisite of this one. Because for this course we will use discrete math, knowledge, scales all the time. Here we need to do it. Counting. Okay. We want to count the number of operations. Number of additions. Let's count number of additions first, then multiplications. Do you know how many additions we need for this problem? I cannot hear your answer, but here, let me just do some analysis. And you can see if you use the same method as mine. All right. Here we need to use a special technique in discrete math, counting technique. Okay. So what kind of counting technique do we need? Here I give you its name, counting by reference. So counting by reference. You may not heard of this name, but its meaning is so obvious. So here, let me explain the meaning of this method. So very straightforward. Yeah. The essence of this method, why this method is so effective. Simple but effective. The reason is this. To apply it successfully, we need to discover an important rule. So that rule is 1-to-1 correspondence. 1-to-1 correspondence between two mathematical objects. What's that? Two mathematical objects. What kind of mathematical objects? Let me explain that relationship. Yeah, let me use the space to explain that two mathematical objects. The first one, object 1, object 2. So here, our goal, we want to count the number of object 1, but it is not easy to count it directly. So here, the number of additions. Suppose some of you do not feel it's easy to count, but some of you may feel it's easy, so you do not need that. But here I talk about the general method. So when you count the object 1, it's not quite easy to count directly. So you want to consider a different mathematical object, and there is a one-to-one relationship between them. One object 1 element corresponds to one object 2 element, and so on. Okay, things like that. It is relatively harder to count the number of elements in object 1, but it is much easier to count the number of elements in object 2. Then, because those numbers are equal, so you can get your answer easily. That's the whole idea. Okay? All right, so let me use this example to explain, to illustrate the effectiveness of this method. All right, we want to count the number of additions in this polynomial. So that's the object. Okay, we treat this as a mathematical object. The addition as the object. Number of elements in this object. Yeah, but suppose it is not so easy to count it directly. Now let's create a one-to-one correspondence with another object. So what kind of, to discover this, you need some insight. You need some sharp insight. Yeah. Here, let me point that out. Look here, there is one addition, right? This plus sign means one addition. Can I connect this plus sign with the subscript A1 subscript? A1 subscript. The first plus sign, I drag it, I point it to plus 1, that's subscript 1. Similarly, the second plus sign, I make it point to subscript 2 of the next term, and so on. So the last plus sign corresponds to the last subscript n. Yeah? Is that a one-to-one correspondence? Yes, that is exactly a one-to-one correspondence. Now, if we count the first object number of elements, not easy, let's look at the number of elements for the second object. Second object, subscripts, right? Subscripts. If we count the number of subscripts, excluding A0, okay? Because there is no plus sign corresponds to A0, so we exclude it. Right. Now we count the number of subscripts that correspond to the plus sign from 1, 2, 3, all the way through n. How many elements in this list? This is a list. How many elements in this list? Is it much easier to count than counting number of additions? Right? So that's the point of this algorithm. That's the, smart way. Remember, I mentioned the smart way. Here, you can feel about it. The smart way. What do I mean, the smart way? This is the smart way. Okay? So we find the answer, the number of additions, n units of time. All right. So we complete this part, 8.3. Okay. All right.